few words about me. I'm an associate professor at the Jagiellonian University when I work with GMUM group, and I'm also a research team leader on IDEAS and CBR. And my research mainly focuses on sustainable artificial intelligence. And in case of Jagiellonian University, I focus more on interpretability, so how to create interpretable models. But in IDEAS, I moved in a little bit different direction, and for a year I started research on sustainable artificial intelligence in autonomous machines. So what's the motivation? The main motivation is that machine learning uses more and more computational power currently. And well, when before the deep learning era, models had, let's say, 1,000 parameters, now there is 1 trillion of parameters in the large language models. So the problem that appears is that current artificial intelligence research produces a big carbon footprint, and the main purpose of sustainable artificial intelligence is to reduce the computation, reduce this impact on the environment. For example, by recycling the models that were trained so far. So at IDEAS, we have a specific group which is dedicated to that kind of solution in computer vision. And this group is called Zero Waste Machine Learning. It is led by Tomasz Zieliński. And this group is mainly focused on two topics in sustainable artificial intelligence. The first one is the subgroup of Bartek Twardowski, which is focused on continual learning. And the second group currently is led directly by Tomasz, focused on conditional computations. Well, when we discussed what should be the topic of the third group, which I am leading, we started to ask ourselves how close we are to reality when we produce our algorithms. Because the thing is that we want to publish in the best conferences, get as much as possible A-star publications, but we in the end have to achieve as good results as possible in benchmark databases. But the question is how far it is from the real applications, right? I think that there is a huge gap between the machine learning research in this area and the robotic research in this area. And this is exactly what we wanted to fill, right? We wanted to fill this gap. We wanted to ask ourselves a few questions. First, do our setup are realistic, right? What is the real energy consumption? And what are other open questions in autonomous machines related to sustainable computer vision? So that's why I decided that the topic of my group will be focused on this direction. I have to say that I'm not a robotic person, you know. We have a specific teams in IDEAS which are dedicated for robotics, for example, Krzysiek Walas. So I look at this, please look at this research as a basic research in machine learning, but dedicated to specific problem of autonomous machines, okay? This is the gap that we want to fill. And well, we started with defining, well, how we see the problem, right? Because we have to somehow put our research in machine learning, so we have to define what topic will appear there. So we just draw a drone, and they did, you know, like fast out-of-box thinking, because for us it was out-of-box because we are getting out from our safe area. You know, we are in machine learning, we have good publications there, but we want to go somewhere else, and it's always somehow uncomfortable. So we said that, okay, when there is a robot, a machine, then there are some limitations in device, right? So there are limitations in power, limitation in processing unit, in memory. That's one inside robot. What other things there appear? Well, multimodality, right? Multimodality is important, and because autonomous machines have various sensors. So that's why we say that it can contain various types of sensors, so multimodal data. And the third limitation is the limitation, what we call environment limitation. So limited labels, restricted field of view, or privacy concerns. And that kind of setup resulted in, well, I just said to my group, we have that kind of setup. We have to think about our research as there is a robot, there is some setup, there is some problem, robotic problem, and this think about your projects, so they focus on that direction, right? And the first project that appeared was the project in the area of active visual exploration. We published the paper on it on IJCAI this year. And the problem was as follows. When there is a human and he goes, right, and we go through the forest or through the garden, we do not analyze everything all the time. We focus our attention on different points which are important to do a task. For example, to go to the park and as fast as possible. So in case of robots, it's a little bit different because the robots observe well, the whole area all the time and process it all the time, right? So the question here is how to actively explore, like a human, right? To focus on the specific points. So we proposed, it's not a new topic, but what we proposed is that the existing methods are very complicated because they use a lot of loss function. The loss function is composed of 5 sub-loss functions that you have to, you know, appropriately balance between each other. So what we proposed is to use only one loss function, so the final loss function that's optimized the final task, but chooses the next observations, right, using the uncertainty of the model, internal uncertainty of the model. And this uncertainty was based on self-attention from transformers. So you can see here how the algorithm look like. We are on the point t equal 2, so we have 2 observations. We have mask autoencoder, and 2 observations go to encoder. We have, well, token representation on the output. Then we add representation of the remaining patches, which are unknown. So this observation is just empty. We have only position is encoded. And we pass it through decoder. It's typical architecture of mask autoencoder. And we obtain the current prediction, right? How, in this case, the task was reconstruction of the image. So based on 2 parts from this, we have that reconstruction. And we also have internal uncertainty of the model. And the model said that in this part, he is the most uncertain. So we choose this part for the next step, and we pass everything through the model again. And we obtain such a prediction using only those 3 parts of the image. So here you can see how it works for 3 different images, right? When we observe new observation, how the prediction changes and how the uncertainty of the model changes. I haven't said that, but it should be quite clear that uncertainty is high in the area of yellow, in the yellow area. So we also, well, compared ourselves with the real input, right? Like how the image looks like, ground truth image. This is our results, and this is a result obtained by other methods. And also for segmentation. In case of segmentation, for example, we were able to, well, obtain a very good view of the windows here. And, well, the results were visually better. And also, there was tables with the result, but I won't show them to you. It's pointless right now. So what we also observed was that current methods that use transformers need, you know, the grid sampling, right? And that was the somehow the question that came up when we made this visual active research. That we would like to have a transformer that obtained any shape of input in any position, right? Not a grid position, but any position, and not a fixed size, but any size, right? So instead of this, we would like to have this as an input, right? The red rectangles. And this work was submitted to SDM. This is a Core A conference. Quite good, but not A star. And what we proposed there, we proposed training where on the input there's an image, and we just, in each iteration step, we applied various augmentations which are responsible for the position, for the, some of the patches are missing, and you can also choose how many of them are missing, and the position elasticity, so we can move the position of the patches. So this is, in the end, the input of the vision transformer, and we generate a prediction. And one thing we found out is that the accuracy, we are able to obtain the transformer, which has much more elastic input, but the accuracy is similar. Our, well, result here is in green, right? So we can see that accuracy is similar, and, well, a little bit lower here, and a little bit higher here. So lower here, because this is, for this number of patches, the VIT transformer was trained, right? And our transformer was trained for various different number of patches, so that's why in some area we obtained better results. And those two, well, things we would like to also adapt to the active visual exploration, so that make it more like realistic. Because when there's example a drone, and if he can zoom in to specific area, then he also can go up and down, so the scale of the parts that he observes will change, right? And also the position of those parts will be different. Another question that appeared when we did this active visual exploration was, do we always have to push all the patches through the network? Or maybe we can recycle the token representations. So here we produced a paper called Token Recycling. This is a CVPR submission. And again here, we assume that we do not have all the patches at the beginning, but we have one patch, right? We put it through some part of the transformer, generate its representation, and then we put the other part of the image also through transformer, generate its representation, and then we can compute the results. So when we have the second part of the image visible, we can reuse this representation which was produced before. We don't have to push everything through the network. And the question here up here, is it possible? Does it work like that in Transformer? And well, what we did is that we checked how it works for basic Transformer, of course, but also how we proposed a different regime of training, where we divide the image, for example, into some number of parts, in this case 2 parts, and we process them separately, right? So the self-activation map is computed only for those 2, not for 4 together, but for those 2 and those 2 separately, right? This decreases the computation in case of Transformer. And then when we have, after some layer of the Transformer, we, well, put them together and process them together on the end, but only on the end. So the number of computation, the size of the attention map is big, but only on the final stage of the Transformer. And what we obtained is shown here. The green curve is our method, right? So we are able to achieve almost as good accuracy as the normal Transformer, but we process the patches separately till 8th block of Transformer. So only in 4 blocks of Transformer they are processed together. And this is how the G-flop was reduced when we did that. There are also other topics that my research team member chose. For example, one of them is federated learning. And in this case, we have some number of clients which achieve the data, collect the data, and there is one model created on the server, right? So, so the idea is to create a model which is good for all the clients, and so they all contribute on generating the model. But we should not be able to regenerate the real images from the representation that we obtain on the server. So there is assumption that clients let us, that users let us to collect the data, but which does not contain the private data, but only the representation, which cannot be used to regenerate the true data, right, the real data. So there is a privacy concern here. The other team the other team member wanted to focus more on the different type of sensors, and so we have a cooperation with IJCAI University, where we work on methods for learning representation for event cameras, right? And we also have a cooperation with Wrocław Polytechnic, where we want to think about cross-model distillation approach. So again, we think about the robot as a unit that have a lot of sensors, right? And they should be able to learn from each other. So that's all from my side. I encourage you to contact me if any of this research was interested for you. And please also check out the website of our group. Thank you very much.